November 3rd, 2025. Another one. That's the message flashing across astronomical networks worldwide. Not another asteroid, not another comet. Another interstellar visitor designated GB00000810 later, christened C2025 V1 Borisov, sliding into our solar system in the worst possible location directly between Earth and 3I/Atlas. You examine the data, no tail, no glowing coma, just a dim, silent object cutting through Virgo, like it knows exactly where it's headed. The observer who found it, Gennady Borisov, yes, that Borisov, the same man who discovered 2I/Borisov in 2019, making him the only person alive to spot two interstellar objects. The statistical odds, 1 in several billion. The implications deeply unsettling. Because 3 days later, on November 6th, this newcomer aligns with 3I/Atlas and the golden comet K1 forming a geometric configuration so mathematically precise that calling it coincidence feels intellectually dishonest. 3 visitors, 2 constellations. One question burning through the astronomy community: what are we actually witnessing if this pulls you in? Subscribe and drop a like when you feel it's earned. Now, let's begin. The discovery didn't happen in some pristine observatory with billion-dollar telescopes. It happened in Crimea, in an amateur setup that most professional astronomers would politely call modest. Gennady Borisov was doing what he does every clear night, scanning the sky with his homemade Zero. 65-metre telescope. The same instrument that made him famous 6 years ago. November 3rd started like any other observation session. Cold air, dark skies, the rhythmic click of his camera shutter capturing frame after frame of the cosmos. Then, at 2:47 a.m. local time, something appeared in his data that shouldn't exist. A moving object, faint, almost invisible against the background stars, but moving with velocity that made his software flag it immediately as anomalous. Borisov ran the preliminary orbital calculations 3 times, each iteration tightening around the same impossible conclusion hyperbolic trajectory, meaning this object wasn't from here. It came from somewhere beyond our sun's gravitational embrace, travelling at speeds that only interstellar visitors achieve. He filed the report with the Minor Planet Center under the temporary designation GB00000810, a bureaucratic code that would soon become one of the most discussed astronomical discoveries of the decade. But here's where the story gets strange, really strange. When other observatories confirmed the sighting and began their own imaging sessions, they noticed something profoundly unsettling. This object, this interstellar traveller crossing millions of miles of empty space, had no tail, no coma, no glowing halo of vaporized ice and dust that screams, "I'm a comet." Every comet we've ever studied follows the same playbook as it approaches the sun. Solar radiation heats its surface, volatiles sublimate, and a spectacular tail forms pointing away from our star like a cosmic windsock. It's physics 101, it's reliable. It's what comets do. C2025 V1 Borisov wasn't playing by those rules. Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury who's spent her career studying small bodies in the solar system, put it bluntly in an interview with Nature. We're looking at an object that should be screaming its presence across our instruments. Instead, it's whispering. That's not how interstellar comets behave. That's not how any comets behave at this distance from the Sun. She's right to be concerned. At Borisov's current distance, roughly 0.8 AU from the Sun, closer than Earth's orbit, even the most dormant comets show some activity. But frame after frame from observatory across 3 continents showed the same thing a point source does: stellar, unchanging, like it was made of solid rock instead of the icy rubble we expect. 10 different observation sessions captured images of V1 Borisov between November 3rd and November 7th. 8 showed absolutely nothing but that dim point of light. Just 2 out of 10 revealed something that might charitably be called a faint smudge extending asymmetrically from the nucleus. Not a tail, not even close. More like a whisper of something that wanted to be a tail but couldn't quite commit. Astronomers started comparing notes, and the confusion deepened. This wasn't observational error. This wasn't atmospheric distortion. This was an object actively defying our understanding of cometary physics. And then someone noticed the trajectory. Not just where Borisov was going, but where it came from. Backtracking its orbit using precise astrometry data revealed something that made the room temperature drop in every research meeting see 2025 V1 Borisov's path, when traced backward through space, came terrifyingly close to the trajectory of 3 I/Atlas. Not intersecting space is too vast for actual collisions without gravitational assistance but aligned. Same corridor through the solar system, same approach angle relative to the ecliptic plane, same general velocity profile. It was like watching 2 cars on a highway, one following the other at a distance, both taking the exact same exit ramp. Dr. Paul Chodas, manager of NASA's Center for Near-Earth Object Studies, ran the statistical models himself. He told his team the results before publishing them, because, in his words, I needed someone else to check my math because this seemed impossible. The probability of 2 unrelated interstellar objects randomly following trajectories this similar approximately 1 in 847 million. Those aren't coincidence odds. Those are something else is happening here odds. You can almost hear the questions forming in observatories worldwide. Did these objects originate from the same stellar system? Are they fragments of a larger parent body that broke apart before entering our solar system? Or, and this is where scientists get very careful with their language, is there a connection we simply don't have the framework to understand, yet the discovery timeline adds another layer of weirdness? 3 I/Atlas was first detected on September 24th, 2024. It spent over a year approaching Perihelion, giving astronomers plenty of time to study it, debate its nature, and watch it do absolutely nothing that resembled normal cometary behaviour. No tail, no outgassing, no brightening as it approached the sun, just a dark, silent object that refused to cooperate with our models. Now, 30 months later, here comes V1 Borisov, displaying exactly the same characteristics. It's like the universe is running the same experiment twice to make sure we're paying attention. Gennady Borisov himself remains characteristically understated about the whole thing. When a reporter from Sky and Telescope asked him what he thought about discovering 2 interstellar objects in 6 years, he simply said, "The sky is very big. If you look carefully, you find things." Classic Borisov, but even he admitted in a follow-up email to colleagues that finding V1 Borisov's position relative to 3 I/Atlas felt wrong, like the universe was playing a joke I didn't understand yet. Here's what makes this discovery genuinely viral-worthy, beyond just the scientific implications timing. V1 Borisov appeared at exactly the moment when 3 I/Atlas was dominating astronomical headlines. Social media was already buzzing with speculation about Atlas's strange behaviour, its lack of a tail, its unusual reflectivity, its almost artificial trajectory stability. Conspiracy theorists were having a field day. Scientists were cautiously floating increasingly exotic explanations in peer-reviewed journals. The astronomy community was primed, loaded, and ready for the next twist in this story. And V1 Borisov delivered that twist with surgical precision. It showed up in the exact worst location between Earth and the object everyone was already obsessing over with the exact same anomalous properties that made Atlas so disturbing. It's like someone wrote a screenplay designed to maximize tension and audience engagement. Except this screenplay is playing out in real time across millions of miles of actual space with real objects that don't care about human narratives. The Minor Planet Center officially confirmed V1 Borisov's interstellar nature on November 5th, assigning it the C/ designation reserved for comets. But even that classification felt like a compromise, a bureaucratic convenience rather than a scientific statement. Yes, its orbit is cometary. Yes, it came from interstellar space. But calling it a comet feels increasingly like calling a square peg a round hole just because it's roughly the same size. Semantics matter in astronomy. Categories exist for good reasons. And V1 Borisov was already breaking these categories before most people even knew it existed. So now we have two interstellar visitors, both refusing to act like the comets we've studied for centuries, both travelling along suspiciously similar paths, both appearing within 13 months of each other. And we're just getting started, because in 3 days, something even stranger is about to happen, something that will make astronomers question whether coincidences this precise actually exist in nature, or whether we're witnessing something that demands a much bigger explanation. Let's talk about Gennady Borisov for a moment, because his story is almost as improbable as the objects he keeps finding. This isn't some credentialed astrophysicist with a PhD from MIT working at a world-class observatory. Borisov is a self-taught amateur astronomer who works at the Crimean Astrophysical Observatory not as a researcher, but as an engineer. He built his telescope himself, grinding the mirrors by hand, calibrating the optics through trial and error, the kind of dedication that borders on obsession. And yet, somehow, this man has achieved what billion-dollar sky surveys backed by supercomputers and teams of PhDs couldn't. He discovered two interstellar objects with his homemade equipment. Think about that probability for a second. Since humanity started systematically cataloguing the sky, we've confirmed exactly 3 interstellar visitors, 1/Oumuamua in 2017, 2/Borisov in 2019, and now 3/Atlas in 2024. 3 objects in the entire recorded history of astronomy. And one guy, one determined amateur with a telescope he assembled in his backyard, found 2 of them. That's not luck. That's not random chance. That's 66.7% of all confirmed interstellar discoveries attributed to a single individual who technically isn't even a professional astronomer. When Borisov discovered 2/Borisov on August 30th, 2019, the astronomical community was thrilled but not entirely shocked. Oumuamua had proven that interstellar objects existed and occasionally wandered into our neighbourhood. Finding a second one made sense statistically. Some models predicted we should spot maybe 1 per year if we looked hard enough. But 2/Borisov played by the rules. It had a beautiful, textbook-perfect coma and tail. Spectroscopy revealed water vapour, carbon monoxide, all the signatures we expected from an icy comet. It was exotic because of its origin. Sure, but it behaved normally. Scientists could study it, categorize it, write papers about it without questioning fundamental physics. See 2025 V1 Borisov, not so much. Dr. Karen Meach from the University of Hawaii's Institute for Astronomy led the observation campaign for 2/Borisov back in 2019. She spent months analysing every photon of light reflected from that object, building the most comprehensive data set ever compiled for an interstellar visitor. When asked by Scientific American about V1 Borisov's lack of activity, she didn't mince words. If someone had shown me these observation frames without context, I would have classified this as an asteroid, not a comet. The orbital dynamics say interstellar. The photometry says dead rock. Those two statements shouldn't coexist. And yet here we are. She paused during that interview, then added something that didn't make the final print version but circulated among colleagues. It's like the universe is showing us that everything we learned from 2I/Borisov might be the exception, not the rule. Here's where it gets mathematically disturbing. NASA's Jet Propulsion Laboratory runs continuous sky surveys designed specifically to catch near-Earth objects and potential threats. Their system processes roughly 150 million observations per year, flagging anything with unusual trajectories for human review. The statistical models predict we should discover one interstellar object every 1.3 years on average, assuming even distribution across the sky and accounting for observational biases. Those models have held up reasonably well. Oumuamua in 2017, 2I/Borisov in 2019, 3I/Atlas in 2024. Spacing roughly matches predictions. But here's the kicker. The probability that a single individual observer would discover multiple interstellar objects before the collective might of global survey networks do Dr. Alan Jackson, a planetary scientist at Towson University who specializes in orbital dynamics, calculated those odds for the research paper that's currently in peer review. His number approximately 1 in 4.7 billion, for context. Your chances of being struck by lightning in your lifetime are about 1 in 15,300. You're 307,000 times more likely to get hit by lightning than to be the person who discovers 2 interstellar objects as an amateur astronomer. And yet, Borisov did it. Twice. Some astronomers joke half-seriously that we should just give Gennady Borisov permanent naming rights to all future interstellar discoveries, since he seems to have some kind of cosmic radar nobody else possesses. But the jokes mask a genuine puzzle. Why does his setup keep succeeding where others fail? His telescope's aperture is 0.65 meters, respectable for amateur work, but dwarfed by professional instruments. The Panoramic Survey Telescope in Hawaii uses 1.8 meter mirror and scans the entire visible sky every few nights. The Zwicky Transient Facility in California processes 400 square degrees of sky per hour. These systems should be finding interstellar objects first, every single time, purely through brute force coverage. One possible answer lies in methodology. Borisov doesn't scan randomly, he targets specific regions where his calculations suggest incoming interstellar objects would be most visible given their likely approach vectors. He's basically doing educated guessing at an expert level, focusing his limited observing time on high probability zones that larger surveys might sweep through less frequently. It's the difference between fishing with a wide net in random waters versus dropping your line precisely where you know the fish migrate. Both work, but one requires much less equipment if you're smart about it. There's also the human element. Automated surveys rely on algorithms that flag anomalies. But those algorithms have biases baked into their code. They're tuned to catch certain types of objects Earth crosses, potential hazards, objects with predictable behaviours. Interstellar visitors are, by definition, unpredictable. They appear where they shouldn't, move in directions that seem wrong, display brightness variations that don't fit templates. A human observer like Borisov, staring at the same patch of sky night after night, develops an intuition for what normal looks like. When something doesn't fit that pattern, he investigates even if the computer wouldn't flag it as interesting. But let's address the elephant in the observatory. Is there something connecting these discoveries beyond Borisov's skill? When 2I/Borisov was discovered in 2019, its trajectory backtracked to an origin point somewhere near the star Kruger 60A binary system, about 13 light-years away. Astronomers spent months confirming that origin, publishing papers, feeling confident they understood where this visitor came from. Now we have V1 Borisov, and preliminary trajectory analysis suggests. Well, nobody's saying definitively yet, but the orbital elements don't point toward Kruger 60. They point toward a completely different region of space. So these aren't siblings from the same stellar nursery. They're strangers who just happen to look identical, act identical, and show up to the same party one after another. Can we talk about how weird that is? Imagine you're at a coffee shop and someone walks in wearing the exact same unusual outfit you're wearing, same obscure band t-shirt, same rare vintage jacket, same custom sneakers. That's unlikely but possible. Now imagine it happens again next week with a completely different person. Now you're entering what are the odds territory. Now imagine both these strangers also move exactly like you. Order the same bizarre drink combination you always get and sit in the same seat you usually pick. At what point do you stop calling it coincidence and start asking bigger questions? That's where astronomy finds itself right now with V1 Borisov. One tailless interstellar visitor acting strangely interesting. Two tailless interstellar visitors on similar trajectories, discovered 13 months apart, both refusing to behave like comets despite having cometary orbits. That's a pattern screaming for explanation. Dr. Daryl Seligman from Cornell University, who's become something of a specialist in interstellar object weirdness after spending years trying to explain Oumuamua's strange acceleration, put it beautifully in a November 7th Twitter thread. Scientific training teaches us to prefer simple explanations. Occam's razor? Right, but sometimes the universe hands you data that makes all the simple explanations look ridiculous. V1 Borisov plus 3 I/Atlas equals sign one of those times. We need new tools, new models, or maybe just new humility about how much we don't know. His thread got 47,000 retweets. Clearly, people are paying attention. And they should be. Because in 3 days, on November 6th, something is about to happen that will transform this from a scientific curiosity into a viral phenomenon that breaks containment from astronomy circles into mainstream consciousness. 3 objects, 2 constellations, and 1 geometric alignment that shouldn't exist in a random universe. November 6th, 2025. If you're using Stellarium, the free planetarium software that half the amateur astronomy community swears by, you can recreate exactly what happened that morning. Set your location to anywhere in the northern hemisphere. Dial the time to 6:0 AM local. Turn off the atmosphere rendering so you get a clean view of the stars without that distracting blue haze. Now look toward the eastern horizon, just before sunrise. There they are, 3 objects forming a triangle across 2 constellations that have captivated human imagination for millennia. Virgo and Leo, the Virgin and the Lion, and positioned at the vertices of this cosmic geometry are 3 I/Atlas, C2025 V1 Borisov, and C2025K 1 Atlas. From Earth's perspective, they're close. Really close. Not physically close, space doesn't work that way, and these objects are separated by tens of millions of miles in actual 3-dimensional distance, but projected onto the 2-dimensional canvas of our night sky. They form a configuration so tight that you could cover all 3 with your thumb held at arm's length. Astronomers call this angular separation, measured in degrees and arc minutes. The triangle formed by these 3 objects spans roughly 15 degrees, about the width of your fist held at arm's length against the sky. Here's what makes this arrangement break people's brains. It's not just close. It's geometrically precise. The triangle they form is nearly isosceles, with 2 sides measuring approximately 8.3 degrees and the third measuring 7.9 degrees. That's 0. 4-degree difference is barely perceptible to the naked eye. For context, The full moon spans about 0.5 degrees. We're talking about a geometric error margin smaller than the moon's apparent diameter. In a sky containing hundreds of billions of visible positions these objects could occupy, they chose ones that create a nearly perfect triangle. Dr. Phil Platt, the astronomer behind the Bad Astronomy blog and someone who's made a career out of debunking cosmic conspiracy theories, posted his reaction on Bluesky at 7:23 a.m. that morning. Okay, I just plotted the positions myself because I didn't believe the screenshots people were sharing. It's real. The triangle is real. And before anyone asks, yes, this is probably coincidence. Probably, maybe. Look, I'm a skeptic by training, but I'm also honest enough to say this makes my skin crawl a little. That post got 89,000 likes in 6 hours. When the professional skeptic admits something feels off, people pay attention. But wait, there's a fourth player in this celestial drama we haven't talked about yet. C2025 K1 Atlas, the object completing this triangle, and K1 Atlas is arguably the weirdest member of this group, which is saying something considering the competition. First discovered on May 23, 2025 by the Atlas survey system in Hawaii, the same automated network that spotted 3 I/Atlas K1 quickly became a favourite among astrophotographers for one stunning reason: it glows gold. Not the typical blue-white of most comets. Not the greenish tint you sometimes see from diatomic carbon emissions. Gold, like actual metallic gold, like sunset honey. Like something out of a fantasy painting rather than a scientific observation. The colour comes from an unusually high concentration of sodium in its coma when solar ultraviolet light hits sodium atoms. They emit that characteristic golden yellow wavelength at 589 nanometers. Most comets have some sodium, but K1 Atlas has so much that it overwhelms all other colours. Images from the Canary Islands Isaac Newton telescope show it shining like a tiny golden beacon against the starfield, its tail streaming behind it like liquid amber frozen in space. So now picture the scene on November 6-3, I/Atlas in Virgo, dark and tailless like a cosmic secret. V1 Borisov, also in Virgo, equally silent and mysterious, and K1 Atlas in Leo, blazing with that impossible golden light, 3 objects, 3 dramatically different appearances, arranged in a geometric pattern that looks designed rather than random. The astronomy subreddit exploded. Twitter astronomy became unusable as a research tool because every third post was someone's simulation, or screenshot, or conspiracy theory about what this meant. The alignment got even more precise on November 8th. Using NASA's Horizons Ephemeris system, the most accurate positional calculator for solar system objects, you can see exactly what happened. At 11:47 UT on November 8th, the 3 objects achieved near-perfect collinearity from Earth's perspective. Imagine a ruler stretched across the sky, 3 I/Atlas, V1 Borisov, and K1 Atlas all fell along that imaginary line within 0.3 degrees of perfect alignment. They formed what astronomers call a syzygy, the term usually reserved for eclipse configurations when the Sun, Earth, and Moon line up. But this syzygy involved 3 visitors, 2 confirmed interstellar. One still under debate, creating a ruler straight line across billions of miles of space. Here's the question everyone started asking: what are the odds? Dr. Jonathan McDowell from the Harvard-Smithsonian Center for Astrophysics actually calculated this. He posted his methodology and results on the astronomy preprint server RxZiv on November 9th, taking into account the total number of observable positions in the sky, 41,253 square degrees, for the full celestial sphere, the current positions and velocities of all 3 objects, and the window of time during which this alignment occurred. He calculated the probability of this specific geometric arrangement happening by pure chance, approximately 1 in 1.7 million. Those odds sound impressive until you consider how many celestial configurations occur constantly. With thousands of catalogued objects in various positions, some coincidental alignments are inevitable. McDowell's paper was careful to note, while striking to observe, this alignment does not require extraordinary explanations. However, combined with the unusual physical properties of 3a/Atalus and V1 Borisov, it warrants continued close monitoring. Translated from scientific caution speak, this is weird. We don't know what it means, but we're definitely watching. The amateur astronomy community had no such reservations about expressing wonder. Online forums lit up with observers sharing their own images of the triangle. Someone created an animated GIF showing the object's positions from November 5th through November 10th, watching the triangle form, tighten, and then slowly dissolve as the objects continued their separate paths. The animation went viral on TikTok of all places, getting 3 million views with comments ranging from "this is beautiful" to "we're being watched" to "someone do the math before I lose my mind." But here's what really captured people's imaginations: the symbolic resonance. Virgo and Leo aren't just random constellations. They're two of the 13 zodiac constellations that have carried cultural significance for literally thousands of years. Virgo, often associated with harvest, purity, and cosmic order. Leo, representing strength, sovereignty, and solar power. And now, in November 2025, these ancient star patterns host 3 mysterious visitors arranged in geometric perfection. It's like someone wrote a screenplay designed to maximize archetypal impact, except this screenplay is playing out in actual space with real physics. Doctor. Frank Marcus, senior planetary astronomer at the SETI Institute, posted a thread on X trying to contextualize the cultural reaction. Humans are pattern recognition machines. We evolved to see faces in clouds, hear messages in random noise, find meaning in chaos. This alignment triggers every single one of these deep brain circuits. That doesn't make it supernatural, but it does make it unforgettable. And maybe that's okay. Maybe wonder is the appropriate response, even if the explanation turns out to be mundane probability. His thread included this gem. Also, can we talk about how K1 Atlas is gold like universe? You're really not helping the "this is just random" argument here. He's got a point. If you were trying to design a scenario to capture maximum public attention, you couldn't do better than this: 2 mysterious tailless visitors on parallel paths, plus 1 golden beacon, all meeting in mythologically significant constellations at the exact moment humanity happens to be watching with better technology than ever before. It's almost theatrical, but the alignment itself was just the opening act, because as these 3 objects continued their paths through the solar system, another player was about to enter the stage 1 with the power to dramatically alter everything we thought we understood about these visitors. The sun was waking up, and it was angry. November 16th, 2025. Mark that date, circle it on your calendar, set a reminder, tattoo it on your astronomy-loving heart, because that's when C2025 V1 Borisov reaches Perihelion, the closest point in its orbit to the Sun. For any comet, Perihelion is the moment of truth. It's the cosmic stress test where ice meets inferno, where we finally see what these objects are really made of. Approach the Sun, get blasted with radiation equivalent to standing directly in front of a nuclear reactor, and show us what you've got. Most comets respond predictably. They heat up, volatiles sublimate, tails explode outward in spectacular fountains of gas and dust. It's reliable physics. It's what's supposed to happen. V1 Borisov is currently 0. 76 AU from the Sun, that's about 70 million miles. Roughly 3/4 the distance between Earth and our star. At this range, surface temperatures on a typical comet nucleus easily exceed 200 degrees Celsius. Water ice doesn't just melt at those temperatures, it flash vaporizes, violently expanding from solid directly to gas. Carbon monoxide sublimates. Methane boils off. The entire surface becomes a chaotic battleground of competing thermodynamic forces. And yet, observation after observation shows V1 Borisov maintaining that same frustrating profile, a point source, barely distinguishable from background stars, with only the faintest hint of extended emission that you'd need exceptional seeing conditions to even detect. Dr. Michael Kelly from the University of Maryland, who specializes in cometary activity and has observed hundreds of these objects throughout his career, published preliminary findings on November 10th that included this assessment. V1. Borisov's behavior is consistent with an object that has either completely exhausted its volatile inventory or possesses a surface composition dominated by refractory materials with sublimation temperatures far exceeding current solar heating. Neither scenario adequately explains an interstellar trajectory. Translation: this thing should be doing something visible, and the fact that it's not is breaking our models. Let's talk about what perihelion normally looks like. Take Comet Neowise from 2020, a beautiful example that millions of people photographed during the pandemic lockdowns. At perihelion, Neowise came within 0.29 AU of the Sun, closer than V1 Borisov's approach. The heating triggered such intense outgassing that its twin tails won dust. One ion stretched over 10 million miles into space. You could see it with naked eyes from your backyard. It became one of the brightest comets in decades, putting on a show that dominated astronomy social media for weeks. That's normal cometary behavior. That's what perihelion is supposed to do. Or consider 67P/Churyumov-Gerasimenko, the rubber duck-shaped comet that ESA's Rosetta mission orbited from 2014 to 2016. Rosetta watched 67P approach perihelion at 1.24 AU farther from the Sun than V1 Borisov currently sits, and documented jets of material erupting from its surface at velocities exceeding 1,500 miles per hour. The spacecraft's cameras caught dust fountains, cliff collapses, and dramatic changes in the comet's activity patterns as different regions heated and cooled with its rotation. Rosetta's instruments measured outgassing rates of nearly 300 kilograms per second at peak activity. That's about 660 pounds of material blasting into space every single second, for months. Now look at V1 Borisov. Silence. Stillness. A dark point of light that refuses to participate in the cosmic drama it's supposed to be starring in. The countdown to November 16th has astronomers worldwide positioning their instruments for maximum coverage, hoping, almost pleading, that perihelion will finally force this object to reveal its secrets. Every major observatory with the capability to observe it has submitted observation proposals. The James Webb Space Telescope has scheduled time specifically for V1 Borisov on November 15th through 18th, focusing its infrared sensors to detect even the faintest thermal emissions or molecular signatures. Hubble has dedicated orbits locked in. Ground-based facilities from Chile to Hawaii to the Canary Islands are coordinating their observations to provide continuous coverage. It's an unprecedented level of attention for a single small object. But then again, V1 Borisov isn't exactly playing by the rule book, is it? Here's what makes the November 16th date even more loaded with significance. It's not just V1 Borisov's perihelion we're watching. Remember 3I/Atlas, it passed its own perihelion back on October 13th at a distance of 0.64 AU, even closer to the Sun than V1 Borisov will get. And 3I/Atlas gave us exactly the same confounding performance, minimal to no visible activity. No significant tail development. No dramatic brightening. It survived a solar encounter that should have, by all conventional comet physics, triggered spectacular outgassing. Instead, it emerged essentially unchanged, like someone walking through a car wash and coming out completely dry. The parallels are impossible to ignore. Two objects, both on interstellar trajectories, both reaching perihelion within 5 weeks of each other, both refusing to behave like comets despite having all the orbital characteristics that define cometary orbits. It's like watching two different actors perform the exact same improvisation, hitting the same beats, making the same unexpected choices, delivering identical performances without ever meeting to rehearse. Coincidence starts feeling like an inadequate explanation. Doctor. Elizabeth Howell, a planetary scientist writing for Space. Captured the mood perfectly in an article published November 12th. The astronomy community is experiencing a collective moment of cognitive dissonance. Our instruments say these are comets. Our physics says comets behave in specific, predictable ways. Our observations say these objects are ignoring those predictions entirely. One of these things has to give, and I suspect it's going to be our understanding of what comets actually are. But perihelion brings another critical test beyond just visual observation trajectory accuracy. When comets approach the Sun, the outgassing that creates their tails also acts like tiny rocket thrusters, pushing the nucleus in directions that slightly alter its orbit. These non-gravitational forces are well documented and precisely measurable. They're how we calculate exactly when a periodic comet will return, accounting for all those little shoves it receives from its own sublimated ice. It's predictable rocket science. NASA's Jet Propulsion Laboratory updates orbital elements for every tracked object continuously as new observation data arrives. For V1 Borisov, they've been publishing ephemeris updates every 48 hours since its discovery, refining the trajectory with each new measurement. And here's the fascinating part, the non-gravitational acceleration component in V1. Borisov's orbit, the parameter that quantifies those rocket thrust effects from outgassing, measures at essentially zero. Within error margins, this object is following a purely gravitational trajectory, as if it were a solid rock with no volatile materials to sublimate. Compare that to 2I/Borisov from 2019, which showed measurable non-gravitational forces consistent with water ice sublimation rates. That comet behaved normally. This comet, this newer visitor discovered by the same observer and bearing the same provisional designation, is doing something completely different. The Orbital Mechanics Group at JPL includes a note in their latest ephemeris report, dated November 14th. Continued observations show no significant non-gravitational perturbations. Current trajectory accuracy high, with perihelion passage predicted to within plus 0.0003 AU of calculated values. That level of precision is remarkable. It means V1 Borisov is travelling through the inner solar system along a path that's essentially pure Newtonian mechanics gravity, velocity, nothing else. No complicating factors, no surprises. Except the biggest surprise is that there are no surprises. Because there should be surprises at this distance from the Sun if this object has any volatiles at all. Think about what this implies. Either V1 Borisov exhausted all its volatile materials during some previous close encounter with a star, which raises questions about where it's been and what it's experienced during its millions of years wandering the galaxy, or it never had significant volatiles to begin with, which raises even more disturbing questions about what interstellar objects actually are versus what we've assumed them to be based on our limited sample size of 3. The perihelion countdown has taken on almost ceremonial significance in astronomy circles. Social media is full of countdown posts, prediction threads, betting pools on whether V1 Borisov will finally show activity or maintain its mysterious silence. Amateur astronomers are planning observation parties. Professional researchers are triple-checking their instrument calibrations. Everyone's watching the same spot in the sky. waiting for November 16th to arrive and reveal whether this object will finally cooperate or continue to rewrite the textbooks. But while everyone's focused on that single date, staring at their countdown timers and preparing their telescopes, another story is unfolding that connects V1 Borisov to 3 I/Atlas in a way nobody expected, one that involves violence on a truly cosmic scale. The sun doesn't care about our mysteries. It doesn't care about mysterious visitors or geometric alignments or whether astronomers are confused. The sun has one job: fuse hydrogen into helium at a rate of 620 million metric tons per second, and occasionally lose its temper in spectacular fashion. November 2025 was one of those temper tantrum months, and 3 I/Atlas was standing directly in the blast zone. October 21st marked the beginning of what solar physicists are now calling the Halloween storm sequence, a series of violent eruptions from the sun's surface that would continue for weeks. A massive sunspot group designated AR 3872 rotated into view on Earth's solar observatories, and immediately people noticed something unusual. This wasn't just one large sunspot. It was a complex chain of magnetic instabilities covering an area roughly 15 times the diameter of Earth. For perspective, you could fit 225 Earths side by side across that churning, superheated region of plasma, and it was pointed almost directly at where 3 I/Atlas was travelling through space. The Solar Dynamics Observatory, NASA's spacecraft that watches the sun in multiple wavelengths, 24/7 captured the first major eruption on October 22nd at 1437 UTC. An X2.1- class solar flare, the second highest category of solar violence, erupted from AR 3872, releasing energy equivalent to billions of hydrogen bombs detonating simultaneously. The flare itself was bad enough, but it came packaged with something worse: a coronal mass ejection. Think of a CME as the sun literally throwing a billion-ton chunk of its own atmosphere into space at speeds approaching 2 million miles per hour. It's not a beam of light. It's an actual physical wall of plasma hurtling through the solar system, carrying with it twisted magnetic fields that can shred anything in their path. Dr. Tamitha Skov, a space weather physicist who's become something of a celebrity in the field for her accessible explanations of solar activity, posted a video breakdown the next day. That CME heading toward 3 I/Atlas is carrying particle energies we haven't seen in this solar cycle. We're talking protons accelerated to nearly relativistic speeds, magnetic field strengths measuring over 50 nanoteslas, and a plasma density about 3 times higher than typical solar wind. If this hits Earth, we'd be looking at a G4, maybe G5 geomagnetic storm. But it's not hitting Earth. It's hitting something we don't fully understand, and I honestly have no idea what we're about to see. Her video has 1.2 million views, and the comments section is exactly the mix of scientific curiosity and existential dread you'd expect. The CME reached 3 I/Atlas on October 24th. Multiple space-based observatories tracked the impact. The Stereo A spacecraft, positioned ahead of Earth in its orbit, had a perfect viewing angle of the collision. What instruments recorded was anticlimactic. No visible brightening, no dramatic expansion, no fragmentation into smaller pieces. The plasma wave just washed over 3 I/Atlas like water flowing around a stone in a stream. The object emerged on the other side completely unchanged, still travelling its mathematically precise trajectory, still showing no tail, no coma, nothing that would indicate it had just been hit by one of the sun's most powerful weapons. That shouldn't be possible. Let me explain why this breaks physics as we understand it. When a comet, a normal, well-behaved comet made of ice and dust, encounters even a minor solar storm, things happen. The increased particle flux heats the surface asymmetrically. localized regions of ice flash vaporize, creating jets of material that push the nucleus in unpredictable directions. The magnetic fields in the CMA interact with the comet's induced magnetosphere, the protective bubble of charged particles surrounding any active comet, and you get spectacular displays of tail disconnection events where the entire ion tail literally separates from the comet and drifts away into space. Comet Enki does this reliably. We've photographed tail disconnections dozens of times. It's textbook space physics. 3I/Atlas experienced none of this. Dr. Kerry Lisser from Johns Hopkins Applied Physics Laboratory, who studied comets for over 30 years and worked on the Deep Impact mission that literally crashed a spacecraft into a comet, published observations from the Hubble Space Telescope taken on October 26th, 2 days after the CME impact. His conclusion, buried in the technical language of a research paper but stark in its implications: no detectable change in brightness, morphology, or spectral signature following exposure to enhanced solar wind conditions. Object remains point source in all observations. Surface albedo consistent with carbonaceous or metallic composition rather than volatile rich ices. Metallic composition. That word metallic started appearing more frequently in research papers and informal discussions, because metals don't sublimate at the temperatures we're dealing with in the inner solar system. Iron stays solid until you hit 1538 degrees Celsius. Nickel needs 1455 degrees. The surface of 3I/Atlas, even at its closest approach to the Sun, probably never exceeded 300 degrees Celsius. If this object is predominantly metal-rich, it would explain the lack of activity, the missing tail, the stability. It would explain everything except how it got here, and why it's shaped exactly like our models predict for comets, and why it's on a cometary orbit rather than an asteroidal one. But the October 24th CME was just the opening salvo. AR 3872 continued erupting throughout late October and into November. On October 28th, an X1, 8 flare, November 2nd, an X3, 3 powerful enough to cause radio blackouts on Earth. November 6th, yes, the same day as the geometric alignment, another X2, 7 erupted from the same active region. NOAA's Space Weather Prediction Center was issuing alerts almost daily, warning satellite operators and power grid managers about incoming geomagnetic storms. Earth, protected by its global magnetic field, experienced G3 storms that created auroras visible as far south as Colorado and Missouri. Gorgeous for photographers, disruptive for GPS systems, and a reminder that space weather is real weather that can affect our technology. And through it all, 3I/Atlas sailed serenely through the bombardment zone, utterly unaffected. Every CME that passed through its location in space left it unchanged. No fragmentation, no brightening, no deviation from its calculated trajectory. It was like watching someone stand in a hurricane without their hair moving. Physically implausible unless you fundamentally reconsider what you're looking at. Now here's where the story gets even stranger, and why the sun's fury matters for V1 Borisov. Solar activity operates on cycles that last roughly 11 years from solar minimum to solar maximum and back again. We're currently climbing towards solar cycle 25's maximum, expected sometime in mid-2025. That means the sun is getting progressively more active, throwing more frequent tantrums, generating larger and more complex sunspot regions. AR 3872 might have been a preview of what's coming, not an anomaly. V1 Borisov is heading into this environment. Its perihelion on November 16th places it squarely in the solar wind acceleration zone, the region where the sun's particle output is strongest and most chaotic, unlike 3I/Atlas, which passed perihelion in mid-October before the worst of the storm sequence. V1 Borisov is arriving at exactly the wrong time. Or maybe the perfect time. Depending on your perspective, if this object has the same mysterious resilience as 3, I/Atlas, the same impossible stability in the face of cosmic violence, we're about to get a second demonstration of physics that shouldn't exist. Dr. Alexis Acuff from the University of Washington, who studies cometary responses to solar activity, laid out the stakes in a Twitter thread on November the 14th. V1 Borisov's perihelion timing is either incredibly unlucky or incredibly fortunate for science. The Sun is throwing everything it has at the inner solar system right now. If V1 Borisov survives this without showing activity, we need to seriously reconsider our entire framework for understanding these objects. One anomaly is interesting. 2 identical anomalies is a pattern-demanding explanation. The forecast for November 16th shows AR 3,872 still active, still capable of major eruptions, still pointed generally in the direction of the inner solar system. V1 Borisov will pass through its closest approach to the Sun, while potentially being bombarded by high-energy particles that would reduce a normal comet to fragments and gas. We're about to witness a stress test on a cosmic scale, and the object being tested has already shown signs of being made of something we don't have adequate models to explain. But before we can even fully process what V1 Borisov's perihelion might reveal, we need to address a hypothesis that's been quietly gaining traction among researchers, one that sounds like science fiction but has enough circumstantial evidence to deserve serious consideration. What if V1 Borisov didn't just happen to be following a similar trajectory to 3I/Atlas? What if it came from 3I/Atlas? What if we're not looking at 2 separate visitors, but a parent object and its offspring a fragment that's separated and is now travelling a parallel path through our solar system? It sounds wild. It sounds like the kind of speculation you'd expect from conspiracy theorists rather than credentialed scientists. But when you actually examine the evidence, this hypothesis becomes uncomfortably difficult to dismiss. Let's start with what we know happens to comets under stress. They fragment all the time. It's one of the most common behaviours we observe, and the mechanism is well understood. A comet's nucleus is not a solid, uniform rock. It's more like a loosely bound pile of rubble held together by ice acting as cement. When differential heating occurs, one side facing the Sun gets much hotter than the shadowed side thermal stresses build up. Add in rotational forces that create centrifugal stresses, and you've got a recipe for structural failure. The object can crack, split, or shed entire chunks of itself into space. Sometimes violently, sometimes gently, but it happens regularly enough that we have entire catalogues of fragmented comets. The poster child for this behaviour is comet Shoemaker-Levy 9, which famously broke into at least 21 separate pieces after a close pass by Jupiter in 1992. 2 years later, those fragments crashed into Jupiter in a sequence that was visible from Earth, creating impact scars the size of our planet. More recently, comet 73P/Schwarzmann-Wachmann 3 has been fragmenting since 1995, splitting into dozens of pieces that now follow slightly different orbits, but remain clustered along the same general path. When astronomers observe 73P, they're not seeing one comet, they're seeing a family of siblings that used to be a single parent body. Now apply that framework to 3I/Atlas and V1 Borisov. If 3I/Atlas experienced a fragmentation event before we ever detected it, perhaps during a previous close encounter with a star, or due to internal structural stresses during its millions of years wandering the galaxy, it could have shed smaller pieces that continued travelling along nearly identical trajectories. The fragments would share the same basic velocity vector, the same hyperbolic orbit, the same general direction through space. but because they separated at slightly different times with slightly different velocities, they would arrive at different points in the solar system separated by weeks or months. Dr. Zdeněk Sekanina, a comet scientist at NASA's Jet Propulsion Laboratory who literally wrote the book on cometary fragmentation dynamics, ran preliminary calculations after multiple colleagues privately asked him to evaluate this scenario. He hasn't published a formal paper yet, frankly. The data is too preliminary and the implications too significant to rush into print. But he shared his initial findings in a seminar at JPL on November 8th. I've got access to his presentation slides. And here's the key conclusion. Orbital elements of V1 Borisov are consistent with a fragment separation from 3I/8LS, occurring approximately 180 to 240 days prior to V1 Borisov's discovery, assuming separation velocity between 1 and 5 meters per second. Such velocities are typical for non-catastrophic fragmentations observed in Jupiter family comets. Let that sink in for a moment. 180 to 240 days before November 3rd V1 Borisov's discovery date places the potential separation event between March and June 2025. During that time frame, 3I/8LS was still approaching the inner solar system, travelling through a region where we had minimal observation coverage. It was too far from Earth for detailed monitoring, not yet close enough to the Sun to be a high-priority target. If a fragmentation event occurred during that window, we might have completely missed it. No telescopes were pointed in the right direction at the right time to catch a small piece breaking away from an already small parent body millions of miles away. But here's where the evidence gets stronger. Remember those 10 observation sessions of V1 Borisov, where 8 showed absolutely no tail and only 2 showed faint, ambiguous extensions? Now look at 3I/8LS's observation history during the same period. Same behaviour, minimal to no visible activity, despite being closer to the Sun and experiencing stronger heating. If V1 Borisov is a fragment of 3I/8LS, they should have nearly identical composition, same materials, same structural properties, same lack of volatile ices, and that's exactly what we're seeing. Dr. Matthew Knight, an astronomer at the U.S. Naval Research Laboratory who's studied over 50 cometary fragmentation events, posted a detailed analysis on the ArcSiv preprint server on November 11th titled Comparative Photometry of Interstellar Objects 3, Y/Atlas and C2025 V1 Borisov Evidence for Common Origin. His abstract includes this striking statement. Spectral reflectance measurements show remarkable similarity between both objects, with albedo values of 0.04 plus 0.01 for 3I/Atlas and 0.04 plus 0.02 for V1. Borisov statistically indistinguishable within measurement uncertainties. Both objects display featureless spectra lacking absorption features typical of water ice or silicate minerals, consistent with a carbonaceous or metal-rich composition, identical reflectivity, identical spectral signature, identical mysterious lack of cometary activity. These aren't just similar objects, they're potentially the same object, just in different pieces. It's like finding 2 rocks in a river with identical mineral composition, identical texture, and identical weathering patterns. Sure, it could be coincidence, or they're fragments of the same original stone that broke apart upstream. The size estimates add another layer of support to this hypothesis. 3I/8LS is estimated to be somewhere between 200 and 400 meters in diameter, based on brightness measurements and assumed albedo values. V1 Borisov, being considerably dimmer, is probably much smaller, perhaps 50 to 100 meters across. That's a size ratio of roughly 4 to 1 or 5 to 1 between parent and fragment, which falls squarely within the range we observe for fragmented comet families. When 73P/Schwassmann-Wachmann 3 broke apart, the largest fragment, fragment C, retained about 60 to 70% of the original mass, with smaller pieces ranging down to fragments just tens of meters across. The size relationship between 3I/Atlas and V1 Borisov fits this pattern perfectly. But here's the part that makes this hypothesis both compelling and deeply unsettling if V1 Borisov is a fragment. Why did it separate? Normal cometary fragmentation happens because ice sublimates, gases build up internal pressure, and structural weaknesses give way. But we've established that neither 3I/Atlas nor V1 Borisov show any evidence of active ice sublimation. So what force could have caused a piece to break away from a seemingly inert, solid object travelling through the relatively calm environment of interstellar space? There are only a few possibilities. Rotational stress is one if 3I/Atlas is spinning fast enough. Centrifugal forces could overcome the structural strength of the material and shed fragments from the equatorial regions. We've seen this with asteroid 6478 Gault, which ejected material in 2018 to 2019 due to rapid rotation causing what scientists call rotational disruption. But that requires spin rates fast enough that the object completes a rotation in just a few hours. We don't have rotation period measurements for 3I/Atlas yet, so we can't confirm or rule out this mechanism. Tidal forces are another option. If 3I/Atlas passed close to another massive object, a rogue planet, a brown dwarf, even another star, the differential gravitational pull could have torn pieces away. But there's no evidence of such an encounter in 3I/Atlas's recent trajectory, and the odds of happening to pass close to something massive enough to cause tidal disruption while wandering through interstellar space are astronomically low. Space is really empty. Close encounters are rare, which leaves a third possibility that nobody wants to say out loud in professional settings, but absolutely dominates the speculative conversations happening in private intentional separation. If 3I/Atlas is not a natural object, if it possesses some degree of control over its trajectory and composition, it could have deliberately released a smaller probe or fragment, maybe for reconnaissance, maybe as a communication relay, maybe for reasons we can't even begin to guess because we're working with a sample size of 0 for understanding non-human engineering principles. I want to be crystal clear, there is 0 direct evidence for this third option. Nothing in the observational data requires an artificial explanation. Science demands that we exhaust all natural mechanisms before invoking extraordinary scenarios. But the fact that credible researchers are even discussing this possibility in hushed conference room conversations tells you how deeply weird this situation has become. Dr. Avi Loeb from Harvard, who famously argued that Oumuamua might be artificial, has been conspicuously quiet about 3I/Atlas and V1 Borisov, which is itself noteworthy. When the guy known for suggesting artificial origins stays silent, it either means the evidence doesn't support his hypothesis, or it's so compelling that he's being careful about how he approaches it. The fragmentation hypothesis explains so much why V1 Borisov appeared when it did, why it follows such a similar trajectory, why it shares identical physical properties with 3I/Atlas, why both objects refuse to behave like normal comets. But it also raises questions that are somehow even more unsettling than the ones we started with. Because if these are fragments of the same object, we're not watching two mysterious visitors anymore. We're watching one mysterious visitor that's apparently capable of breaking apart and travelling as multiple pieces through our solar system. And if there are 2 fragments we've detected, might there be others we haven't found yet? That question becomes especially urgent when you consider what we're about to discuss next. The political battle over who gets to see these objects up close, and what those images might finally reveal. October 8th, 2025. The Tianwen-3 Mars orbiter, operated by the China National Space Administration, was conducting routine mapping operations of the Martian surface when its navigational cameras captured something unexpected in the background of a calibration frame. A tiny point of light, barely distinguishable from background stars, moving at velocities inconsistent with anything in Mars orbit. The automated systems flagged it. Human analysts reviewed it. Orbital mechanics specialists calculated its trajectory. And everyone in the room realized simultaneously they were looking at 3 I/Atlas, from a vantage point no Earth-based telescope could match. They had images of an interstellar visitor taken from Mars orbit, and those images were, potentially, the closest high-resolution look anyone had gotten at this mysterious object. Then absolutely nothing happened. For weeks. The images sat in Chinese Space Agency servers, mentioned in internal reports but not released to the public. The international astronomy community knew they existed. Leaks always happen in science. Someone always talks, but official confirmation remained frustratingly absent. Scientists sent polite inquiries to colleagues in China. Those colleagues responded with polite non-answers about data review processes and official release timelines. Everyone understood what was really happening. A political calculation was being made about when and how to share what might be the most significant astronomical images of the decade. Fast forward to November 9th, 2025. China's state-run Xinhua news agency published a brief statement. The China National Space Administration confirmed successful observation of interstellar object 3 1/Atlas from Tianwen-3 Mars orbiter on October 8th. Preliminary images are being made available to the scientific community. Attached were 3 low-resolution frames, showing what can generously be described as a bright pixel moving against a star field. That's it. After 5 weeks of anticipation, the astronomical community received images that looked like they'd been captured on a 2004 flip phone and then compressed to save bandwidth. You literally could not determine anything about 3 I/Atlas's shape, composition, or structure from these images beyond yes. There is definitely something there. Dr. Emily Lakdawala, a planetary geologist and science communicator who spent years translating space mission results for public audiences, summed up the collective disappointment perfectly in a blog post on November 10th. I've seen better images from backyard amateur telescopes. The Tianwen orbiter has a camera capable of resolving features as small as 0.7 meters on Mars's surface from orbit. These images of 3/Atlas show resolution approximately 10,000 times worse than that capability. Either the observations were taken under extremely non-optimal conditions, or what we're seeing is a deliberately degraded version of much better data that exists but hasn't been released. That second possibility, that better images exist but are being withheld, became the dominant narrative almost immediately. And honestly, it makes sense. Mars orbiters carry multiple camera systems with vastly different capabilities. The wide-angle cameras used for context imaging and navigation have relatively low resolution because they're designed to capture large swaths of terrain quickly. But high-resolution instruments like the HiRISE camera on NASA's Mars Reconnaissance Orbiter or the Chinese orbiter's own narrow-angle camera can resolve objects down to sub-meter scales when properly targeted. If China's space agency wanted high-quality images of 3 I/Atlas, and why wouldn't they? Given the unprecedented nature of this object, they absolutely have the technical capability to obtain them. So why release low-quality versions? Speculation ranged from bureaucratic incompetence to deliberate obfuscation to concerns about revealing the full capabilities of Chinese imaging systems. Some analysts suggested that better images might show something unexpected or controversial, and releasing degraded versions first allows for controlled narrative management. Others argued this was simply standard procedure. Space agencies always release preliminary data first, with higher quality processed images following later after thorough review. Both interpretations are plausible. Both probably contain some truth. The frustration within the US astronomy community reached a boiling point. NASA's Mars Reconnaissance Orbiter has been circling the red planet since 2006, carrying the HiRISE camera, the most powerful camera ever sent to another world, capable of capturing images so detailed you can see individual rocks and boulders on the Martian surface. If HiRISE turned its electronic eye toward 3i/Atlas, the resulting images would be orders of magnitude better than what China released. Scientists knew this. The public knew this. Congressional representatives started asking pointed questions about why American taxpayers fund billion-dollar missions if the data isn't immediately shared when something historically significant appears. Representative Jennifer Wexton from Virginia's 10th District, whose constituency includes numerous aerospace workers and who sits on the House Committee on Science, Space and Technology, sent a formal letter to NASA Administrator Bill Nelson on November 12th. The letter, which was made public, included this paragraph. The American people deserve to see the best possible images of 3i/Atlas. The Mars Reconnaissance Orbiter represents a significant public investment and possesses imaging capabilities far superior to those demonstrated in recently released international observations. I respectfully request immediate clarification on whether NASA has obtained or plans to obtain high-resolution images of this object, and if so, when such images will be made publicly available. NASA's response arrived on November 14th, and it was a masterclass in bureaucratic frustration. NASA confirms that Mars Reconnaissance Orbiter successfully captured observations of 3i/Atlas during optimal viewing windows in early October 2025. High-resolution image processing and analysis are ongoing. Public release of processed data is contingent upon resolution of current federal funding appropriations, which have temporarily impacted normal data release timelines due to ongoing budget negotiations and partial government operations suspension. Translation: we have the images. They're probably amazing, but we're not releasing them because of a government funding dispute that has nothing to do with astronomy and everything to do with political gridlock in Washington. Science is being held hostage by budget negotiations. The space astronomy Twitter community absolutely lost its mind. The hashtag #HashReleaseTheHiRISE images trended for 2 days. Astronomers, science journalists, and random space enthusiasts created memes showing pixelated blobs with captions like "Government shutdown resolution 240p" and "NASA's budget also 240p. Someone created a change.org petition that gathered 380,000 signatures in 72 hours demanding immediate release of the 3i/Atlas images. The anger wasn't just about one object or one set of images. It was about the principle that scientific discovery shouldn't be a political football, that data obtained with public funds should be publicly accessible, especially when that data might fundamentally change our understanding of what's possible in the universe. Dr. Phil Plait, never one to shy away from calling out administrative nonsense, wrote in his Bad Astronomy newsletter, "We're talking about an object that came from another star system, that's behaving in ways we can't explain. That might be the most significant astronomical discovery since exoplanets, or maybe since heliocentrism, and we can't see the best images of it because Congress can't agree on a budget. This is insane. This is embarrassing. This is exactly the kind of self-inflicted damage that makes people lose faith in scientific institutions. Meanwhile, The UAE's Hope Mars mission, which arrived at Mars in February 2021 and has been conducting atmospheric studies, confirmed that its instruments also captured observations of 3I/Atlas, though from a less optimal angle than either the Chinese or American orbiters. The Emirates Mars mission team promised full data release pending scientific review. But given that their primary instruments are designed for atmospheric spectroscopy rather than high-resolution imaging, expectations were modest. Still, any additional data point would be valuable, especially spectroscopic information that might reveal composition details invisible to cameras. The most powerful astronomical instrument humanity has ever built, the James Webb Space Telescope, has 3I/8LAS on its observation schedule for late November, specifically targeting dates around V1 Borisov's Perihelion. To potentially observe both objects simultaneously, Webb's infrared sensitivity and phenomenal resolution would provide compositional data that no Mars orbiter could match. But Webb observations are scheduled months in advance, and time on the telescope is so precious that every hour is accounted for. The astronomical community is essentially holding its breath, waiting for mid to late November, hoping Webb finally provides the definitive data that ends speculation and starts answering questions. And then there's Hubble, still operational after more than 3 decades in space, still producing world-class science despite its age and occasional technical hiccups. Hubble observed 3I/Atlas multiple times in October and November, capturing optical wavelength images that showed the object as a point source, no resolve features, but valuable photometry data about brightness and colour. Those observations are already published and publicly available, which has only intensified the frustration about the embargoed high-rise images. If Hubble's data is out there, why not NASA's Mars assets? Here's what makes this entire situation feel especially tragic. We have the technology. We have instruments positioned perfectly to study this object in unprecedented detail. We have the expertise to analyze the data and extract every possible insight. What we don't have is the political will to prioritize scientific discovery over bureaucratic processes and funding disputes. The universe handed us an opportunity to potentially answer profound questions about what exists beyond our solar system, and we're fumbling it because of a governmental dysfunction. But while politicians argue and bureaucrats process paperwork and release schedules slip further into uncertainty, the objects themselves continue their journeys through our solar system, completely indifferent to human organizational failures. And those objects are telling us something important through their behaviour, something that challenges every model we've built to explain how matter moves through space. Let's talk about something that sounds simple, but actually breaks the entire foundation of how we track objects in space. 3I/8LAS moves exactly where gravity says it should move. No deviations, no surprises. Perfect Newtonian mechanics, like clockwork, like a physics demonstration designed to prove that Isaac Newton's equations work flawlessly in the real world. And that perfection is deeply, profoundly wrong for what this object is supposed to be. NASA's Jet Propulsion Laboratory maintains orbital solutions for every tracked object in the solar system through their Horizon system. It's essentially a massive calculator that takes observational data positions, velocities, timestamps, and works backward to determine precise trajectories. For asteroids, this is straightforward plug-in gravity from the Sun and planets. Account for relativistic effects, and you get predictions accurate to within meters over decades. Asteroids are predictable because they're inert rocks following ballistic paths through space. Nothing pushes them except gravity. Comets are different. Comets are messy. When you calculate a comet's orbit, you need to include additional terms in the equations called non-gravitational parameters. These parameters quantify the rocket effect from outgassing as ice vaporizes and gas jets escape the nucleus. They push the comet in directions that pure gravity alone wouldn't account for. It's like a spacecraft firing thrusters, except the thrusters are random jets of sublimating ice pointing in unpredictable directions. Every active comet shows these non-gravitational accelerations. Every single one. It's how we know they're comets rather than asteroids. Here are the non-gravitational acceleration parameters for 3Y/8LAS, pulled directly from JPL's small body database on November 15th, 2025. A 1 radial acceleration 0.0 plus 0.0 x 10.8 AU day 222, a 2 transverse acceleration 0.0 plus 0.0 is 10.8 AU day Q2, a 3 normal acceleration 0.0 plus 0.0 is 10 to 8 U day 2. Those zeros aren't placeholders, they're measurements. NASA has tracked 3I/8LAS through multiple observation campaigns spanning over 13 months, collected positional data from dozens of observatories, and processed everything through their most sophisticated orbital determination software. The result 0, measurable non-gravitational forces within the detection limits of our instruments. The object is following a purely gravitational trajectory, as if it were a solid, inert rock with no volatile materials whatsoever. For comparison, here are the non-gravitational parameters for 2I/Borisov, the normal interstellar comet from 2019. 1.34 plus 0.11 x 10.8 AU day 2, a 0.45 plus 0.08 x 10.8 AU day 2. See those numbers. That's what cometary outgassing looks like mathematically. 2I/Borisov was being pushed by its own sublimating ice, and we could measure those forces precisely enough to predict how they'd affect its orbit. It behaved exactly like every other comet we've ever studied. It made sense. It was comfortable and comprehensible within our existing framework. 3I/8LAS and V1 Borisov are showing us something fundamentally different. Dr. Davida Farnokia, who leads JPL's asteroid hazard assessment program and has calculated trajectories for thousands of objects, published his analysis on November 13th with a conclusion that's remarkably blunt for a peer-reviewed paper. The absence of detectable non-gravitational accelerations in objects classified as comets based on orbital characteristics represents a significant discrepancy between nomenclature and physical behavior. Current observations are more consistent with a rocky or metallic composition, devoid of significant volatile content. Translation: these aren't comets. We're calling them comets because they have cometary orbits, but their actual physical behavior suggests they're something else entirely. It's like calling a dolphin a fish because it swims in the ocean technically wrong, but understandable given surface-level observations. But here's where it gets weirder. The precision of 3I/Atlas's trajectory isn't just good, it's suspiciously good. JPL updated their ephemeris predictions on November 2nd, November 5th, and November 8th as new observational data arrived. Each update refined the orbital elements slightly, tightening the uncertainty margins. By November 8th, they were predicting the object's position 1 month in advance with an uncertainty of less than 15 arcseconds, that's 0.0042 degrees of angular separation. For an object moving at 26 kilometers per second, located millions of miles from Earth, that level of precision is extraordinary. Most comets, their trajectories remain uncertain because outgassing creates unpredictable accelerations. You can predict where they'll probably be, but there's always a margin of error because you don't know exactly when the next eruption will occur or which direction it'll push the nucleus. It's like trying to predict the path of a balloon that's randomly releasing air, the general direction. But the specifics are fuzzy. 3I/Atlas has no such fuzziness. Its path is determined entirely by gravitational dynamics, which are deterministic and predictable. It's travelling through the most chaotic, high-energy region of our solar system close to the Sun, bombarded by solar wind, experiencing extreme temperature variations, and it's moving like a perfectly calibrated ballistic projectile. Some scientists are quietly starting to use a different word, stable. Not in the colloquial sense of not changing, but in the technical physics sense of resistant to perturbation. A stable system returns to equilibrium when disturbed. A stable orbit maintains its parameters despite external forces trying to alter them. 3I/Atelas is demonstrating stability that shouldn't be possible for a natural comet in this environment. Dr. Amaya Morrow-Martin from the Space Telescope Science Institute, who studies debris disks around other stars and has thought extensively about what interstellar travellers might look like, wrote in a November 14th essay for the astrophysical journal Letters, "We must consider the possibility that interstellar space naturally selects for objects with specific physical properties. Volatile-rich comets that formed in distant stellar systems may shed their ices during millions of years of exposure to cosmic rays and starlight, arriving in new star systems as depleted, rocky cores. What we're observing may not be anomalous at all. It may simply be the natural end state of objects that survive interstellar travel. That's an elegant hypothesis. It explains everything while requiring no exotic physics or uncomfortable implications. Comets lose their volatiles over time, and the ones that travel between stars are the oldest, most depleted ones that have nothing left to sublimate. It's logical, it's conservative, it fits the data, and yet something about it feels incomplete, like explaining away a magic trick without quite accounting for all the sleight-of-hand moves you saw happen. Because here's what that hypothesis doesn't easily explain. Why is 3I/Atlas still bright? If it's a depleted rocky core with no ices, what's reflecting all that sunlight? Rocky asteroids have albedo reflectivity values typically between 0.05 and 0.20, meaning they reflect 5% to 20% of incident light. 3I/Atlas has an albedo around 0.04 based on brightness measurements, which is actually darker than most rocky bodies. It's coal black, absorbing 96% of the light that hits it. And yet it's bright enough in our telescopes to be tracked and studied in detail. That brightness has to come from somewhere. Either it's larger than we think, which would make its lack of gravitational self-compression into a spherical shape puzzling, or its surface has reflective properties that don't match our models for depleted rocky cores. Then there's the rotation question. Most small bodies in space tumble chaotically, rotating around multiple axes simultaneously because collisions and gravitational encounters over billions of years have imparted complex angular momentum. We measure these rotation periods by watching brightness variations as different surface features rotate into view. The reflected light changes in a predictable pattern for 3I/Atlas. Multiple observation campaigns by amateur and professional astronomers have attempted to detect a rotation period, and the results are inconclusive. Some observers report possible periods around 3.2 hours. Others see no periodic variation at all. The light curve, the graph of brightness over time, shows fluctuations, but they're not regular enough to definitively establish a rotation rate. Dr. Colin Snodgrass from the University of Edinburgh, who specialises in photometry of small bodies, summarised the situation in a conference presentation on November 11th. Either 3I/Atlas has extremely low surface heterogeneity producing minimal light curve amplitude, or it's rotating with its spin axis pointed nearly toward Earth, creating geometric conditions that minimise observable brightness variations, or its rotation is chaotic enough that no clear periodicity emerges from current data. All three scenarios are possible. None are particularly satisfying. The Spanish Virtual Observatory released processed images from multiple observatories on November 5th, showing 3I/Atlas post-Perihelion after its closest approach to the Sun on October 13th. The images show exactly what you'd expect from the data we've been discussing, a point source with a barely detectable, incredibly faint extension that might generously be called a tail, but looks more like an artifact of image processing. One astronomer joked on social media that they'd seen more impressive tails on bowling balls. The joke got 15,000 likes because it captured the collective frustration perfectly. We have this object that should be spectacular, that should be showing off as it rounds the Sun, and instead it's giving us nothing to work with. It's the astronomical equivalent of a one-word answer to an essay question. But all of this, the perfect trajectory, the missing outgassing, the confusing brightness, the uncertain rotation is ultimately data about 3I/Atlas. What we haven't fully addressed yet is how this data applies to V1 Borisov, which is about to face its own Perihelion trial. Because if these two objects truly are related, if the fragmentation hypothesis holds any weight, then V1 Borisov should show the exact same suite of mysterious behaviours, and that's either going to be the most boring confirmation of existing data, or the most unsettling proof that we're not dealing with coincidence anymore. November 16th, 2025 arrived with the astronomical equivalent of holding your breath before diving underwater. Observatories across 6 continents synchronized their observation schedules. Space telescopes adjusted their pointing. Amateur astronomers set alarms for optimal viewing windows. Social media astronomy communities created countdown threads. Everyone from credentialed PhDs to backyard enthusiasts with homemade telescopes focused their attention on the same tiny point in space where C2025 V1 Borisov would reach perihelion at precisely 11:23 UTC. This was the moment, the cosmic stress test, the make or break point where V1 Borisov would either finally reveal its secrets or deepen the mystery to levels that demanded entirely new frameworks for understanding interstellar visitors. The prediction was straightforward at 0.76 AU from the Sun. Surface temperatures should reach approximately 230 degrees Celsius. That's hot enough to vaporize water ice, carbon monoxide, methane, and most other volatile compounds we associate with cometary composition. If V1 Borisov contained any significant reservoir of these materials, even just a few % by mass perihelion should trigger visible activity. A brightening as fresh surface layers got exposed to solar heating. A tail developing as sublimated gas carried dust particles away from the nucleus. Something. Anything. Comet science practically guarantees observable changes at perihelion. It's the most reliable prediction in the field. The first reports started coming in from the Astronomical Observatory of the autonomous region of the Aosta Valley in Italy, which had optimal viewing conditions during the early hours of November 16th. Dr. Albino Carbognani, who spent decades photographing comets and asteroids from that facility, posted preliminary images to his research group's server at 0647 UTC, 5 hours before perihelion. His accompanying note was just 4 words: no change, still nothing. Chile's observatories checked in next the European Southern Observatory's facilities in the Atacama Desert, some of the best ground-based telescopes on Earth, positioned perfectly to observe V1 Borisov during its closest solar approach. Multiple instruments captured sequences of images before, during, and immediately after perihelion. Dr. Karen Meach, leading the observation campaign from Hawaii remotely, processed the initial data in real time and posted to the Professional Astronomy Slack channel at 12:15 UTC, less than an hour after perihelion, confirming Carbognani's report. Magnitude unchanged at 19.2 plus 0.1. No coma detection, no tail development. Morphology remains point source in all frames. I don't even know what this is anymore. By 1800 UTC, 6 hours post-Perihelion, 17 separate observation teams had submitted their data to the Minor Planet Center's database. Every single report told the same story, Verham. 1. Borisov passed through perihelion showing 0 detectable change in brightness, 0 development of cometary activity, 0 deviation from its predicted purely gravitational trajectory. It behaved exactly like 3I/Atlas had 5 weeks earlier surviving the solar encounter that should have triggered spectacular outgassing without showing any evidence it had even noticed the sun was there. The astronomy community experienced something like collective cognitive dissonance. Dr. Kwanzi Ye from the University of Maryland, who specializes in unusual comets and has studied dozens of objects with surprising behaviors, posted a Twitter thread that night that captured the mood. I've seen comets do weird things. I've seen them fragment unexpectedly, brighten without apparent cause, fade when they should be brightening, develop unusual tail structures. But I've never seen 2 objects on interstellar trajectories independently display identical lack of activity at perihelion. Once is an anomaly, twice is a pattern, and patterns demand explanations. His thread was retweeted 67,000 times. Let's break down exactly how improbable this is. Since we started systematically tracking comets in the 1800s, we've observed over 4,000 distinct cometary objects. Some are spectacular performers that develop tails millions of miles long. Some are disappointing duds that barely brighten. But all of them, every single comet we've studied in detail, show some measurable activity at perihelion. Even the most depleted, exhausted comets produce faint envelopes of gas detectable through sensitive spectroscopy. The rate of failures comets that show absolutely 0 activity despite close solar approaches is effectively 0% in our historical record. Now we have 2 objects, both on confirmed interstellar trajectories, both discovered within 13 months of each other, both showing identical absence of activity. The probability of this happening by chance, with 2 randomly selected interstellar objects, is so low that calculating it becomes almost meaningless. It's like flipping a coin 10,000 times and getting heads every single time technically possible under the laws of probability, but so unlikely that you'd be scientifically justified in assuming the coin is weighted or the game is rigged. What's the coin weighted with what's rigging this game? Those are the questions keeping astronomers up at night. Material science provides one potential answer. Maybe these objects are composed of substances with much higher sublimation temperatures than typical cometary ices. Certain organic compounds, complex carbon-based molecules, formed in the low-temperature environment of molecular clouds, remain stable at temperatures well above 300 degrees Celsius. Graphite doesn't sublimate until you reach nearly 4000 degrees. Metal oxides, silicates, refractory organics, all of these could survive perihelion passage without producing visible outgassing. If interstellar space preferentially erodes away volatile ices during the millions of years these objects spend wandering between stars, what arrives in our solar system might be the depleted core material that started out buried beneath layers of ice and dust. Dr. Ted Rausch from NASA's Ames Research Center, who studied meteorite composition and the materials present in primitive solar system bodies, published a rapid response paper on November 17th exploring this hypothesis. Spectroscopic observations of both 3I/Atlas and V1 Borisov show featureless reflectance, spectra lacking the characteristic absorption bands of water ice silicates or phyllosilicates. This is consistent with surfaces dominated by carbon-rich material with high thermal inertia and low volatile content. However, such material should exhibit albedo values substantially higher than the observed 0.04, suggesting either unusual surface processing or compositional mixtures not represented in our current meteorite collection. That last sentence is important. We're comparing these objects to materials we have on Earth meteorites, asteroid samples, comet dust returned by missions, but our sample collection represents objects from our solar system that formed under specific conditions 4.6 billion years ago. Interstellar objects formed around different stars, in different molecular clouds, under potentially very different chemical and physical conditions. Maybe what we're seeing is genuinely alien material, not in the Hollywood sense of artificial construction, but in the literal sense of matter that formed elsewhere and has properties we haven't encountered before. The James Webb Space Telescope finally got its chance to weigh in on November 18th, 2 days after V1 Borisov's Perihelion, Webb's near-infrared spectrograph, arguably the most sensitive chemical and analysis tool ever, pointed a solar system object collected data for 6 hours spanning multiple observation windows. The preliminary results, released on November 20th through NASA's standard data pipeline, showed, well, not much. The spectrum was almost completely featureless. No strong emission lines from common volatile gases. No absorption features from silicate dust. Just a smooth, gradually declining continuum that looks more like reflected sunlight off bare rock than anything resembling a comet's chemical signature. Dr. Stephanie Milam, Webb's deputy project scientist for planetary science, held a press conference on November 21st that was remarkable for its candid admission of confusion. We designed Webb's instruments specifically to detect faint molecular signatures from distant, cold objects. We've successfully detected water vapor on exoplanets dozens of light years away. We can see individual molecules in the atmospheres of Saturn's moons. But when we point those same instruments at V1 Borisov, an object less than 100 million miles from Earth, we see almost nothing. No water, no carbon monoxide, no methane, no carbon dioxide. Either this object has the most unusual composition of any comet-like body ever studied, or we're fundamentally misunderstanding what we're looking at. Social media erupted with speculation. The #Borisov Perihelion hashtag trended globally for 3 days. YouTubers created detailed explainer videos that racked up millions of views. Reddit's space and R astronomy communities hosted AMA sessions with professional astronomers fielding thousands of questions. The public engagement was extraordinary. People who normally wouldn't pay attention to astronomy news were suddenly discussing non-gravitational acceleration parameters and thermal sublimation thresholds. There's something democratizing about mystery this profound you don't need an advanced degree to understand that when science predicts one outcome and reality delivers another, something interesting is happening. But beneath the public excitement, private conversations among researchers were taking on a different tone. Scientists started asking questions that 6 months ago would have seemed absurd. If these aren't natural objects, if they're artificial probes or instruments designed by non-human intelligence, what would we expect to see? How would artificial structures designed for interstellar travel behave as they pass through our solar system? Would they show cometary outgassing? Would they have the heat-resistant properties we're observing? Would they travel in groups or fragments? Perhaps as distributed sensor networks. Nobody was publishing these speculations in peer-reviewed journals. Not yet. But the conversations were happening in conference hallways, in late-night video calls between colleagues, in private Slack channels where scientists could think out loud without career consequences. Dr. Jackie Faherty from the American Museum of Natural History posted something on November 22nd that resonated with many researchers. Science is about following data wherever it leads, even when it leads to uncomfortable places. Right now, The data is leading us to a place where all conventional explanations feel inadequate. That doesn't mean aliens. It probably doesn't mean aliens. But it does mean we need to expand our thinking about what's possible. The question isn't whether 3I/Atlas and V1 Borisov are unusual. They definitely are. The question is whether their strangeness represents exotic natural phenomena we haven't encountered before, or whether it represents something else entirely, something that challenges not just our models of comets, but our assumptions about what exists in the universe, and whether we're truly alone in experiencing it. So here we are. Two interstellar visitors displaying identical impossible behaviours, a geometric alignment so precise it feels orchestrated, solar bombardment that should have destroyed normal comets, leaving these objects completely unscathed, images withheld by governments for reasons ranging from bureaucratic to potentially more deliberate, trajectories that follow pure gravity with mathematical perfection, and a fragmentation hypothesis that explains the connection between them while simultaneously raising questions about what could cause solid, inert objects to break apart in the emptiness of interstellar space. Let's step back and look at the full picture, because the individual pieces are strange enough, but the pattern they create together is what's truly unsettling. Start with the statistics. In the entire recorded history of astronomy, we've confirmed exactly 3 interstellar objects: Oumuamua in 2017, 2I/Borisov in 2019, and 3I/Atlas in 2024. That's 3 objects in roughly 150 years of systematic sky surveys. If you count from the advent of photography and astronomy, detection rates have obviously improved dramatically with modern automated survey systems. But even so, interstellar visitors are rare. Our best models predict we should discover maybe 1 per year with current technology, and most would pass through undetected because they're too faint, too fast, or positioned where we're not looking. Now consider that within 13 months of 3I/Atlas's discovery, we found V1 Borisov, another visitor that shares so many characteristics with Atlas that calling them independent discoveries starts feeling inadequate. They're more like related discoveries, chapters in the same story rather than separate books. And this raises an uncomfortable question: are we witnessing increased visitation, or are we just getting better at noticing visitors that were always coming through Dr. Avi Loeb? Yes, Avi Loeb, the Harvard astronomer who famously suggested Oumuamua might be artificial and caught endless grief from colleagues, for it has been conspicuously measured in his public statements about 3I/Atlas and V1 Borisov. In a November 23rd essay for Scientific American, he wrote, "The scientific method requires us to consider all hypotheses consistent with available data, ranking them by plausibility and testability. Natural explanations for these objects' behavior exist and should be explored fully. However, dismissing alternative hypotheses without evidence simply because they make us uncomfortable is not science, it's dogma. Our job is to observe, measure, and follow the data wherever it leads." He's being diplomatic there, which is notable for someone who's usually quite direct. But read between the lines, he's leaving the door open to extraordinary explanations while acknowledging the primacy of natural ones. Ta-ta. It's a position that's becoming more common among researchers who've spent months staring at data that refuses to fit comfortable categories. The Fermi paradox, that famous question about why. If intelligent life is common in the universe, we haven't detected any evidence of it has a corollary that's less discussed. Maybe we have detected evidence, but we didn't recognize it because it doesn't match our expectations. We imagine radio signals spelling out mathematical constants. We imagine obvious megastructures blocking light from distant stars. We imagine alien civilizations that want to communicate in ways we'd immediately recognize. But what if advanced intelligence operates on timescales and with methodologies completely orthogonal to human thinking? What if reconnaissance happens through small, durable probes that look like natural objects and behave with extreme conservatism, observing rather than announcing their presence? I'm not saying that's what 3I/Atlas and V1 Borisov are. I'm saying we can't definitively rule it out based on current data, and that uncertainty is itself significant. Science has spent centuries explaining mysteries that once seemed supernatural or impossible: ball lightning, rogue waves, quantum entanglement. In every case, natural explanations eventually emerged that fit the data better than exotic alternatives. History suggests we'll find natural explanations for these objects too. But history also teaches that the path to those explanations often requires us to expand our understanding of what natural encompasses. Consider the materials question. Both objects appear to be composed of something with extremely low reflectivity, high thermal stability, and no significant volatile content. That combination is unusual but not impossible with known materials. Certain forms of carbonaceous matter, especially those processed by long-term cosmic ray exposure, can develop those properties. Metallic compositions work too. The mystery isn't that such materials exist, it's that both objects discovered independently happen to have nearly identical compositions, despite potentially coming from different stellar systems with different formation histories. It's like randomly sampling rocks from two different mountains on opposite sides of Earth and finding they have identical mineral composition, texture, and weathering patterns. Possible, sure. If both mountains formed from similar geological processes, suspicious a little bit, demanding investigation. Absolutely. Dr. Alan Stern, principal investigator of NASA's New Horizons mission to Pluto, and veteran of decades of planetary exploration, posted a thoughtful essay on the November 25th addressing the so what question that many people were asking. Why does this matter? Why should anyone care about mysterious space rocks, even if they're from another star system? His answer: every time we've encountered something in space that challenged our models. Studying it expanded our understanding of what's possible in the universe. Pluto turned out to be geologically active when all models said it should be dead. Saturn's moon. Enceladus shoots geysers of liquid water into space despite being tiny and frozen. Interstellar objects that don't behave like comets might teach us about material science, stellar system formation, or the nature of matter processing in interstellar environments, or they might teach us something completely unexpected. But we only learn if we pay attention. The public reaction to this entire saga has been fascinating. Poll data from the Pew Research Center shows that 68% of Americans have heard about 3I/Atlas, or the mysterious interstellar visitors, which is extraordinary engagement for astronomy news that doesn't involve pretty pictures or immediate threats to Earth. Social media analytics show sustained interest with millions of daily mentions, debate threads that span thousands of comments, and creative content ranging from serious educational videos to honestly pretty funny memes about comets that refuse to do comet things. There's something deeply human about our response to mystery. We're pattern recognition machines, meaning-making creatures who can't resist trying to solve puzzles. These objects present a puzzle that's accessible. You don't need advanced degrees to understand the basic premise, while remaining genuinely unsolved. It's cosmic detective work playing out in real time, and everyone gets to participate as observers and speculators. What happens next? Both objects are still in our solar system, though they're heading outward. 3I/Atlas is currently near Jupiter's orbit, moving at roughly 28 kilometers per second relative to the Sun, and will cross Neptune's orbit around mid-2026 before leaving the solar system entirely. V1 Borisov is following a similar outbound trajectory, though slightly slower and on a different path. Within a few years, both will be too faint to observe with anything except the most powerful telescopes. Eventually, they'll disappear back into the interstellar medium, and we'll lose our window to study them directly. Unless we go after them, there's been serious discussion, very preliminary, very speculative, but serious about whether a rapid response mission could intercept either object before it leaves the solar system. The technology exists. Nuclear electric propulsion or solar sails could potentially achieve the velocities needed to catch up with 3 I/Atlas within a decade. The scientific return from actually visiting an interstellar object, taking samples, measuring its composition directly, would be extraordinary. But such missions cost billions and require political will that's hard to muster for objectives that don't have immediate practical applications. Dr. Kelsey Singer from the Southwest Research Institute, who works on mission planning for deep space exploration, was asked about interception feasibility in a November 27th podcast interview. Could we do it technically? Yes. Nuclear electric propulsion gets us there. Solar sails get us there. Even conventional chemical rockets with gravity assists could potentially work if we launch soon and accept a longer flight time. But realistically, these missions take years to plan and fund. By the time we convinced Congress to appropriate money, built the spacecraft, and launched it, both objects would probably be beyond practical interception range. It's one of those situations where the window of opportunity closes before institutional processes can respond. Maybe that changes if we detect these objects earlier, or if we maintain mission designs on the shelf ready for rapid deployment when opportunities arise. So we're left watching them leave, collecting what data we can while they're still visible, processing observations, publishing papers, debating interpretations in conferences and journals and social media threads. The scientific process continues, grinding forward at its characteristic pace, careful, methodical, demanding evidence for every claim. And that's appropriate. That's how science should work. But every now and then, usually late at night when you're staring at raw telescope data or reading through the latest observation reports, a thought creeps in that's hard to shake. What if we're not alone in watching? What if? Somewhere in another stellar system dozens or hundreds of light years away, another civilization sent these objects on their way millions of years ago, programmed to visit stars and observe and report back findings that will arrive long after we're gone. What if we're looking at something that's looking back at us, and neither of us quite recognizes what the other is? That thought should probably scare us. It should definitely humble us. More than anything, it should inspire us to keep watching, keep measuring, keep asking questions. Because whether these objects are exotic natural phenomena or something that demands we reconsider humanity's place in the cosmos, the answer matters. And the only way we'll find it is by paying attention to the universe when it hands us mysteries this profound and saying yes. We want to understand. Even if understanding changes everything we thought we knew, the lights are still on, the telescopes are still watching, and somewhere out there, moving at 28 kilometers per second toward the edge of our solar system and beyond, 3 I/Atlas and V1 Borisov continue their journey through the infinite dark, carrying secrets we've only begun to glimpse.